A good morning to you wherever you are, and I want us to proceed with our discussion in chemistry. We had begun discussing a topic called acids, bases, and salts, and I want us to proceed with that discussion and be able to move on to something else. I had to introduce to you bases because we had actually discussed acids in our previous discussion where we defined what an acid is. We went ahead and looked at some of the properties of an acid in terms of the way the acids can be able to react to different compounds in chemistry. And to begin with, we are going to first introduce bases. And I'm first going to actually allow ourselves to actually discuss this by having a base getting defined first. And of course, a base can get defined as a substance that can turn, so you can be able to say a substance that can turn a moist red litmus paper blue. A substance that can turn a moist red litmus paper blue can get referred to as a base. Someone else can define a base as a proton acceptor. It means it accepts a proton, unlike an acid which donates a proton. So a proton acceptor is a base, while a proton donor is an acid. So we can be able to actually explain this by using a chemical equation in as far as Bronsted-Lowry theory is concerned. We said that if you have something like dilute hydrochloric acid and you're adding this acid onto water so that the acid can get dissolved in the water. So this is an aqueous acid getting added onto a liquid like water, which is a solvent. It's called a universal solvent used for different purposes in as far as chemical reactions are concerned. And you end up having products as hydroxonium ions. So this is called hydroxonium ions. Hydroxonium ions, then plus chloride ions. What has happened here? We have two hydrogen atoms here, and we are taking one hydrogen atom from the acid and adding onto this water molecule so that the hydrogen atoms end up becoming three. So two hydrogen atoms plus one hydrogen atom to give us three hydrogen atoms plus the oxygen in the water molecule. So when a hydrogen atom is transferred to a water molecule, we end up forming a hydroxonium ion. So these are hydroxonium ions and these are chloride ions. Once the HCl has lost the hydrogen, it ends up getting reduced to the chloride ions. So look at that. So in other words, what you're going to actually have here is this. The water molecule has accepted the hydrogen atom. As you can see, the hydrogen atom has been transferred to the water molecule from the hydrochloric acid. We end up forming the hydroxonium ions with three hydrogen atoms. So this water molecule can be called a proton acceptor and thus qualifies to be our base. It has accepted a hydrogen atom from the acid. So this one qualifies to be called a proton donor because it has donated a hydrogen atom. So at the end of the day, we form what we call a hydroxonium ion. So this is called a Bronsted-Lowry base. Bronsted-Lowry base, Bronsted-Lowry acid. So this is going to be a Bronsted-Lowry acid. It has donated a hydrogen atom. It is a proton donor. This one qualifies to be called a Bronsted-Lowry base. It is a proton acceptor. It has accepted a hydrogen atom from the acid to form the hydroxonium ions. Now, just in case you may consider this backward reaction from this end to this other end, what are we going to have? We shall actually come here and ask ourselves, what has happened? You see, this was a chloride ion only getting formed. But you can decide to have this chloride ion gaining a hydrogen for us to have the HCl. Where has this hydrogen come from? The hydroxonium ion can decide to donate a hydrogen to the chloride ion. So we take one hydrogen atom from this hydroxonium ion, then we add on to the chloride ion for us to form the HCl. Look at that. So this has again accepted a hydrogen atom from the hydroxonium ion. So when H is added on to Cl, we form HCl. So this one becomes Bronsted Lowry conjugate base. Because for the backward reaction, it has accepted a hydrogen atom to form HCl. So Cl plus H is HCl. So it has accepted a hydrogen for the backward reaction. It becomes now the Bronsted Lowry conjugate base. Look at that. But now for this backward reaction, these H3O positive, the hydroxonium ions, have lost a hydrogen atom, have donated a hydrogen atom to the chloride ion. For this backward reaction, they end up losing a hydrogen to end up having two hydrogen atoms. So from 3 to 2. After losing for the backward reaction, this hydroxonium ion can actually get called Bronsted Lowry conjugate acid. Bronsted Lowry conjugate acid. To whoever he has donated to for the backward reaction gets called Bronsted Lowry conjugate base. That becomes the difference between those two very, very, very important parts of the acids and the bases. So we've said a base is a substance that can turn a moist red litmus paper blue. And again, a base is a proton acceptor. It accepts a proton. And in this case, we've actually given an example. For the forward reaction, the H2O, the water molecule, accepts a hydrogen from the acid to form hydroxonium ions with 3 hydrogen atoms. From the 2 hydrogen atoms found in the water molecule, we end up forming what we call hydroxonium ions. This gets called a Bronsted Lowry base. It has accepted a hydrogen atom. The one that has lost gets called Bronsted Lowry acid. For the backward reaction, this one donates and this one accepts. So the one that accepts becomes now the base. So for the backward reaction, you can call it Bronsted Lowry conjugate base. The one that donates that atom to the other species for the backward reaction, this one now donating this to this, can now be able to get called the Bronsted Lowry conjugate acid. Bronsted Lowry conjugate acid. So for that, we can be able now to give a definite definition, a concrete definition of what a base is. So we can be able to actually say that a base is a substance that you can be able to dissolve in water. And at the end of the day, you'll actually get hydroxonium ions if it's an acid and hydroxide ions if it's a base as the only negatively charged ions in that solution. So a substance that can dissolve in water to give, see, hydroxide ions as the only negatively charged ions. A substance that can dissolve in water to give hydroxide ions as the only negatively charged ions. So for us to proceed forward, I would want us to actually give an example that can practically be able to explain to us this definition. We can be able to say we have sodium hydroxide as a good example of a base. So this is let's take it to be a solid for that matter. And then you're actually going to dissolve this solid in water and see which properties will it actually end up giving us. So in this case, the sodium hydroxide is a base. It being a base, it will end up dissolving in the water molecules that we're actually using here as our solvent to give us sodium ions, which are positively charged, and hydroxide ions, which are negatively charged. So aqueous, then aqueous. So from the look of things, you realize that the sodium hydroxide can qualify to be called a base because it has actually dissociated or ionized, you see, in water to give us hydroxide ions as the only negatively charged ions. So any substance in chemistry that you can dissolve in water, then it will end up dissociating to give you hydroxide ions as the only negatively charged ions in that solution will qualify to be called a base. So a base must first dissociate or ionize in water, then it must end up giving you hydroxide ions as the negatively charged ions in that solution. So those are just some of the definitions you can be able to come across in as far as bases are concerned. And preferably, you should note this. You should note this. You can also be able to get both strong bases and weak bases. We might look at that later on, but please note this. You have something called ammonia solution or ammonium hydroxide. This is also a base. Once this substance also gets dissolved in water, for your information, it's a liquid. Let's take it to be a solid as well. So we're going to get ammonium ions, which are positively charged, and hydroxide ions, which are negatively charged. So aqueous, then aqueous. What comes into your mind? The ammonium hydroxide we are taking as our base in this case has only dissociated in water and decided to give us ammonium ions, which are positively charged, and our usual hydroxide ions, which are negatively charged. As long as they have given us hydroxide ions, it will qualify to be called a base. It will qualify to be called a base. Now, let me come back and look at something different from this end. And what I want to look at is this. What are some of the general properties of acids? General properties of acids. General properties of acids. If I can go to something else, as far as strength of acids and bases is concerned. Now, in a layman's language, you can talk about strength of acids and bases. But first, what could be the general properties of these substances, both acids and bases? For your information, you'll realize that, as we have said, an acid must turn a moist litmus paper, which is blue in color, to red. It must turn a moist blue litmus paper to red for it to qualify to be called an acid. So it must turn a moist blue litmus paper. A moist blue litmus paper to red. A moist blue litmus paper to red. Then number two, it must be able to have a pH that starts from 0 to 1 to 2 to 3, you see, to 4 to 5, then to 6. I'll be able to expound more on this by looking at what you call a pH chart. A pH chart. And someone told me somewhere that if you have to talk about a pH chart, we can either be able to have something of this sort. So if I actually find that a substance has a pH ranging from, let's say, 1, 2, 3, 4, 5, 6, then just before 7, look at that. Anything that starts from 1, 2, 3, 4, 5, 6, then before 7, that tells you up to 6.9. That has to have what you call an acidic property. So if substances have n of this pH, either 1, 2, 3, 4, 5, or 6, or 6.9, but less than that, it will qualify to be called an acid. It qualifies to be called an acid. Very good. Now, something else, apart from changing a litmus paper from blue to red or having a pH ranging from 0, 1, 2, 3, 4, 5, 6 up to 6.9, we can also say that acids are good electrolytes, What does that tell you about electrical conductivity? It means that if I take a substance like hydrochloric acid and I actually dissolve this substance in water and the substance ionizes or dissociates, then that means that substance is going to give me hydrogen ions and chloride ions. When these hydrogen ions and these chloride ions are actually able to form part of the solution, then that means the substance will end up conducting electricity or allowing electric current to pass through it. So the substance such as hydrochloric acid, which is actually a solid, or let's say aqueous, then you've added water. You're going to get hydrogen ions and chloride ions. So this is aqueous and this is aqueous. At the end of the day, we've had a chance of having hydrogen ions and chloride ions. These two ions are going to make this substance to be a good conductor of electricity. So an electrolyte is a substance that can allow current to pass through it. And when current passes through it, the substance becomes dissociated or ionized. So a substance that can get decomposed or dissociated when a current passes through it is called an electrolyte. I repeat, a substance that can get decomposed or dissociated into its ions or constituent ions when a current passes through it is called an electrolyte. So preferably, it can allow current to pass through it. When current passes through it, it gets decomposed or dissociated. Let's say, for example, you have HCl, hydrochloric acid, as an example of an acid, and current has passed through it. Look at that. This is current, electricity. When the current passes through it, this substance can allow current to pass through it. When current passes through it, it actually dissociates that substance into hydrogen ions and chloride ions. Look at that. So the ability to allow current to pass through it makes it to become a good conductor of electricity. It actually becomes an electrolyte. It allows current to pass through it, then it becomes a good conductor of electricity. Okay, generally again, we said that acids can be able to react with metals. I guess I must have said this at one point. So we've said acids allow current to pass through them. They become decomposed or dissociate. When they dissociate, they form hydrogen ions and chloride ions, depending on the type of acid you're talking about. So they dissociate or decompose when current passes through them, and that means they can allow current to pass through them. They become electrolytes. They can allow current to pass through. They can become good conductors of electricity. Okay, to move forward, we've actually to note that an acid, when reacted with a metal, as I have actually said in my previous chemical properties of acids, to form a salt plus hydrogen gas. So an acid can react with a metal to form salt and hydrogen gas. An acid reacts with a metal to form salt and hydrogen gas. That's what you actually need to know. I must have talked about this. HCl plus, let's say, a metal like sodium. You're going to get sodium chloride plus hydrogen gas. Pretty so sure about that. So we are going to have this as our chemical equation. Aqueous, solid, aqueous, then a gas. We've actually looked at this, so it may not be so new to you. We've also said that an acid can combine. I have already looked at this chemical property. Let me just give a summary. Can combine with a metal carbonate. So let's say metal carbonate to give us salts, carbon 4 oxide plus water. I have also said that an acid can react with a metal hydrogen carbonate to give again salts, carbon 4 oxide plus water. Regardless of these parts, be it a metal carbonate or a metal hydrogen carbonate, the products are the same. The products are the same. And again, to move forward, you can also note this. You can actually realize that when an acid reacts with a base can be soluble or insoluble. Let's talk about a soluble base. Pretty sure the products are salt and water. Look at that. Or preferably, an acid is reacting with a base and the base is insoluble. Expect the same products. You'll also get salt plus water. For those who went through a topic called acids, bases, and indicators in Form 1, and chemical families and structure of an atom and the periodic table in Form 2 can actually be able to attest to this, that these are the products you're supposed to get when these reactants are put into consideration. And these reactants are put into consideration. When these reactants are put into consideration. Okay, let's look at some of the general properties of bases. So, general properties of bases, something very important to us. General properties of bases. This is very, very important to us. General properties of bases. Number one, I would actually say that bases are able to turn, number one, moist, red litmus paper blue. Correct. Number two, bases must have a pH ranging from, let's say, 8, 9, 10, 11, 12, 13, and 14. I'll be able to lay more emphasis on the strength of bases and acids and be able to give it appropriate pH values for those different categories of compounds. And we shall actually be able to say that energy that starts from 7.1 going forward, it must turn out to be basic, because anything at 7 is neutral. And now beginning from 7.1 going forward up to 14, that substance becomes basic. So bases have pH values ranging from 8 to 14. So 8, 9, 10, 11, 12, 13, and 14 are pH values on a pH scale that are associated with bases. An advantage as well to those doing electrical engineering is that bases are good electrical conductors. So in other words, they can serve as electrolytes. That is to tell you that if I take a compound like sodium hydroxide, look at that, or I take a compound like calcium hydroxide, which is also called select lime, and this one is called caustic soda, and I allow current to pass through them. This is current passing through them. They actually dissociate. Look at that. They actually dissociate, and on dissociating, they'll actually be able to decompose and give us sodium ions and hydroxide ions, calcium ions, correct, and hydroxide ions. So aqueous, 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 and aqueous. So a base can conduct electricity. Current can pass through that base and that base can dissociate or decompose and give us its constituent ions. Sodium hydroxide, also called caustic soda, can dissociate to give us sodium ions and hydroxide ions. Calcium hydroxide, also called select lime, can also dissociate when current passes through it to give us calcium ions and hydroxide ions. So they can conduct electricity. Why? They are what you call mobile ions or free ions. Whenever current passes through a compound and that compound dissociates or decomposes and gives us ions, and the ions can get referred to as mobile, then that means those ions can carry charges. When they carry charges, they can transfer current from one part to another within a particular environment. So these substances can qualify to be called electrolytes because one, current can pass through them, they can get decomposed, then they give ions. Those ions are called mobile ions or free ions or delocalized ions. And those ions can allow current to pass through a substance from one point to another. Why? Because they carry charges. And that is actually what you call electrical transfer from one point to another. Electrical transfer from one point to another. Now to proceed forward, what are some of the other properties of bases? You can also be able to actually put into this discussion that bases are able, one, so a base can react with an acid. At the end of the day, it will give us salt and water. A base can react with an acid, and whatever we get is salt and water. Whatever you get is salt and water. So preferably, those are just some of the properties of bases. Of course, bases can react with metal carbonates, and neither can it give us a chance to have a discussion getting given as far as the bases reacting with metal hydrogen carbonates. But you see, bases are of two main categories. You see, bases can either be metal hydroxides or metal oxides. Look at this. For example, magnesium hydroxide, and then let's say we have calcium oxide. All of them are bases. All of them are bases. Why? Because whenever hydroxide ions are present in a compound, that substance becomes a base. But now, I also actually told students somewhere that metal oxides are bases. Because when I take calcium oxide, then I dissolve it in water. What do I get? I get calcium hydroxide. You see? So this is a metal oxide, which is a solid, getting dissolved in a liquid like water, which is a universal solvent, to give us calcium hydroxide. And calcium hydroxide is a base, which is a weak base. You see? So metal oxides can also be bases. Why? Once they dissolve in water, they give us alkaline or basic solutions. So they can qualify to be called bases. In other words, when they get dissolved in water, they give hydroxide ions as part of the compound you're actually forming. On the product side, I've told you whenever hydroxide ions are present in a compound, that compound must at one point be able to become basic or alkaline. So bases such as metal oxides can get dissolved in water and they can give us basic or alkaline solutions. Basic or alkaline solutions. I'll move forward to something else. And whatever I want to go to is strength of acids and bases. Strength of acids and bases. And we shall be able to actually just summarize this using two very important examples. Let me say I'm going to consider dilute hydrochloric acid and oxen or oxalic acid or octadecanoic acid or hexanoic acid or heptanoic acid or pentanoic acid or nonanoic acid ethanoic acid, propanoic acid, any of them can actually serve us. And now we shall actually be able to actually have this arrangement. Just maybe explain this in a better way. I can have this one as my beaker. Okay, let me just draw it somewhere else to make it very clear to us. Let me see if it is clear. Yeah, I think it is okay. Yeah, so can proceed. So we have this one as our arrangement, and we have maybe two rods. Yeah, these are mostly tested in our examinations, so we're supposed to be able to understand how we can be able to maneuver around and get the right answers for these concepts. So you can have here our switch. You can have here maybe so a voltmeter can be here, or yeah, you can put your voltmeter. Okay, then you can have our battery. Correct. So you can put here this, and then you can have maybe these ones as platinum electrodes. So you can either use platinum or carbon electrodes. Preferably, whatever you may want to use will depend on one, the availability of those electrodes and how cheap or expensive they are. And as far as electrochemistry is concerned as a topic in Form 4, you'll realize that most people resort to using carbon or graphite electrodes because they are one, cheaper, then they are readily available. Unlike the platinum electrodes, which are more expensive and they are not readily available. So to proceed forward, I might want to actually have this as water plus HCl. That is hydrochloric acid. Yeah, it's clear. Water plus HCl or hydrochloric acid. So we want to ask ourselves, when I take HCl, okay, and I dissolve it in water, and this is going to be aqueous, then I have to end up having hydrogen ions and chloride ions. Then I take another acid like ethanoic acid. From organic chemistry 2, you must have been taught on how to get the chemical formulae of different organic acids. See, so that may not be so new to you, or different mineral acids. So when this one also gets dissolved in the water, you're going to get CH3COO negative. It's a bit different because it begins with a negative, then H positive. Correct. So H positive. So aqueous, 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 then aqueous. So the hydrochloric acid has dissociated in the water to give us hydrogen ions, then chloride ions. The ethanoic acid has dissociated in the water as well to give us ethanoate ions and hydrogen ions. Okay, you are wondering between these two, which one is a strong acid and which one is a weak acid? Now, a simple definition or explanation to this. This one is a strong acid and this one is a weak acid. Let's begin from there. There's a strong acid and this is a weak acid. How do I know that a substance is a strong acid? Listen, if I begin from 0, if that can work as my scale on a pH scale, and I find that a substance has a pH ranging from 0, 1, 2, then 3, preferably any substance whose pH has 1 to 3 is a strong acid. Whatever may have a pH of 4, 5, and 6 it qualifies to be called a weak acid. Correct. So I have a substance, and the reading on the pH scale gives me 1, 2, or 3. That must be a strong acid. If the other substance, on the other hand, ends up giving me a pH of 4, 5, and 6, that must be a weak acid. So strong substances, in terms of their acidity, will have pH values of 1, 2, 3. Then weak acids will always have pH values of either 4, 5, or 6. So I expect HCl to be in this category as an example of a strong acid. Then the other one, which is ethanoic acid, to be here. Okay, why would HCl be a strong acid in this case? I've given an example of water getting used as a solvent where the HCl acid dissociates into the water. Or preferably, I can just allow this to be my battery or the power source. This I've told you is a voltmeter to measure the amount of current passing through it. This is our switch that must get closed before current can flow through this arrangement. Okay, I told you these one are electrons. This can just be a beaker or a container to hold our setup. So we might actually eliminate the concept of having water in this arrangement if battery cells are going to be used. And in this case, I will decide to say that when the switch is closed, look at that. When the switch gets closed, the power is able to actually move along this electric circuit. When the power or current reaches into this HCl solution, which is aqueous, the current dissociates this into hydrogen ions and chloride ions. There is complete dissociation. There is complete dissociation. So you actually had hydrochloric acid as our solution in this arrangement. We allowed the battery cells to produce power or current. The current is allowed to pass through this arrangement because of the switch getting closed. The current dissociates or decomposes the acid or the solution into hydrogen ions and then chloride ions. And the dissociation is complete or wholly or fully. You see? So you can say HCl, look at that. And then there's current passing through it. And this makes the HCl to dissociate completely into hydrogen ions and chloride ions. So the dissociation is wholly or it occurs completely or it occurs fully. So hydrochloric acid is a strong acid. Its pH value can either be 1, 2, or 3. But again, why is it a strong acid? It dissociates completely. It decomposes completely. It ionizes completely. It dissociates wholly or it dissociates fully to give us hydrogen ions and chloride ions. So if hydrochloric acid is dissociating wholly, completely, or fully, it will give more hydrogen ions. And that makes it to have a lower pH. And the lower the pH, the stronger the acid. I repeat, I allowed current to pass through hydrochloric acid. You see, the current wholly, completely, or fully ionized or decomposed or dissociated. Look at that. Current passed through HCl wholly, completely, or fully ionized it, decomposed it, or dissociated it as an acid to give more hydrogen ions. And the more hydrogen ions, the lower the pH, 1, 2, 3. And the lower the pH, the stronger the acid or the substance in terms of its acidity. So what is a strong acid? Listen to my definition. A strong acid like HCl is a substance that has a lower pH, like 1, 2, 3. But why? Because when current passes through it, or when the substance gets dissolved in the water, look at that, it ionizes or decomposes or dissociates wholly, completely, or fully to give more hydrogen ions. To give more hydrogen ions. Look at that. To give more hydrogen ions. Very good. And the more the hydrogen ions, the greater the reading on the voltmeter, because that translates into a larger current. So if I end up having the acid decomposing, dissociating, or ionizing completely, or fully, or wholly, and the acid ends up giving more hydrogen ions, then that means we shall have a greater reading on the voltmeter. Look at that, a greater reading on the voltmeter. Or if I have an ammeter, we shall have what we call a greater deflection on the ammeter. You see, so I'll have this. I have this one as my ammeter, and this may be the reading. So let's have something like maybe 1, 2, then 3, then 4, then 5, then 6. So when there is much current resulting from the complete dissociation of the acid, then we shall have what we call a greater deflection on this ammeter. So the ammeter deflects from 0 up to a value like 6. So the greater the deflection on this ammeter, the greater the concentration of hydrogen ions and the complete dissociation of the acid, and the stronger the acid. I guess that makes sense. So a substance whose aqueous solution, so look at this, I've told you that when the acid allows current to pass through it and it becomes wholly, completely, or fully dissociated, it will give more hydrogen ions. And the more hydrogen ions, the stronger the acid and the lower the pH. And the greater the reading on the voltmeter, because that is current, or the greater the deflection on the voltmeter or the ammeter. And remember still, you shall have what you call a greater deflection on the galvanometer. So you can have a greater deflection on the galvanometer, or a greater deflection on the ammeter, or a greater reading on the voltmeter. Or if a bulb is used, there will be a greater extent of the brightness on the bulb. Why? The acid is completely ionized or completely dissociated, giving more hydrogen ions. And the more the hydrogen ions, the larger the amount of current, the stronger the acid, the lower the pH, and a greater deflection on the ammeter, a greater reading on the voltmeter, a greater deflection on the galvanometer, and the brighter the bulb. I guess you can get these questions in the examination, and please be keen on how you're going to answer them as far as this area is concerned. So a greater reading on the voltmeter, a greater deflection on the ammeter, a greater deflection on the galvanometer, and the greater the brightness of the bulb if the acid is going to be stronger, because it will be completely dissociated or ionized to give more hydrogen ions. Correct. So a greater deflection on the ammeter. That makes sense. A greater deflection on the ammeter. So an acid which dissociates or ionizes completely in water to give a higher concentration of hydrogen ions is going to be called a strong acid. But an acid which ionizes in water to give a smaller concentration of hydrogen ions, so smaller concentration of hydrogen ions, should obviously be a weak acid. For example, ethanoic acid is a weak acid. Why? When it dissolves in the water or gets dissociated by a current, it might not dissociate completely. It dissociates partially, and it gives a smaller concentration of hydrogen ions. So it qualifies to be called a weak acid. Why? Because it does not dissociate completely. You get the point? So I can come here and say that ethanoic acid, look at that. on dissolving in water or allowing current to pass through it, dissociates partially. Because we still have some hydrogen ions here, so it has not dissociated completely. So if it does not dissociate completely, then that means some hydrogen ions are still remaining in the acid. So this is a weak acid. It dissociates partially, incompletely. You get the point? So if it dissociates partially or incompletely, then that means it will give rise to few hydrogen ions. Look at that. This is a weak acid. So it must have a pH of around 4, 5, or 6. Why? But it has to actually end up giving us this property. It will dissociate partially or incompletely to give few hydrogen ions. It will give few hydrogen ions in our discussion here. The few hydrogen ions, the smaller the extent of deflection on the ammeter. Look at that. The smaller the extent of deflection on the ammeter, or the less brighter the bulb is going to be, or the smaller the extent of deflection on the galvanometer, and the smaller the reading on the voltmeter. The weaker the acid, the smaller the concentration of hydrogen ions getting produced after partial dissociation. And the smaller the deflection on the ammeter, the smaller the reading on the voltmeter, the smaller the deflection on the galvanometer, and as well the less brighter the bulb. Those are the differences between those two very important concepts that I want you to actually get hold of, because they're going to help you somewhere in as far as this topic is concerned. So acids can be stronger or weak depending on their pH and the ability to dissociate completely or partially. For example, I guess you need to know this. Hydrochloric acid is a strong acid. That means it will completely dissociate on getting ionized. Sulfuric 6 acid is also a strong acid. It will also dissociate completely. Then nitric 5 acid is also a strong acid. It will also dissociate completely. So these are examples of strong acids that a student is supposed to get associated with. But some of the weak acids I can also be able to come across in chemistry can be the weak carbonic acid. Look at that. So this is hydrochloric acid, sulfuric 6 acid, and nitric 5 acid, strong acids. Then weak acids can be weak carbonic acid. You can have what you call sulfuric 4 acid, because this is sulfuric 6. It's a strong acid. Sulfuric 4 acid is a weak acid. Then nitric 3 acid is also a weak acid. You see? Nitric 3 acid. Then you have what you call phosphoric 5 acid is also a weak acid, or phosphoric 3 acid is also a weak acid. So you can either talk about weak carbonic acid, the one used in writing rings, sulfuric 4 acid or sulfurous acid, then nitric 3 acid or nitrous acid, you have what you call phosphoric 5 acid, then phosphoric 3 acid. Those are examples of weak acids. That means they will ionize or dissociate partially in water to give few hydrogen ions. That means they will actually result into a lower current, giving a smaller deflection on the ammeter, a smaller deflection on the galvanometer, making the bulb to be less brighter, and as well having a smaller reading on the voltmeter. Now, in terms of the bases, bases can also portray the same aspect. How? If I use an example of sodium hydroxide or potassium hydroxide, and I decide to actually have them getting ionized, look at that. I expect to have this as my products at the product side of these equations. So I have aqueous, then aqueous. Sodium hydroxide and potassium hydroxide caustic soda and caustic potash are strong bases. Why? When they get ionized, when they get dissociated or decomposed, they give rise to a higher concentration of hydroxide ions. Look at that. When they get ionized or they get dissociated or they get decomposed, they give rise to a higher concentration of hydroxide ions. And the greater the concentration of hydroxide ions, the greater the deflection on the galvanometer, the greater the deflection on the voltmeter. Look at that. The brighter the bulb and the greater the reading on the voltmeter. So when we have a higher concentration of hydroxide ions, then that substance becomes a strong base. Look at that. And it will make the meter to have a greater deflection or reading, the ammeter to have a greater deflection or reading, the voltmeter to have a greater reading or deflection, the bulb will be brighter, and as well the galvanometer to have a greater reading or deflection. And bases which are stronger will have a pH ranging from 12, 13 to 14. So any substance that has a pH ranging from 12, 13 and 14 must be a strong base. Look at that. And I've given examples of sodium hydroxide, caustic soda, and potassium hydroxide, caustic potash. But any value that has to actually end up being 8, 9, 10, or 11 will be a pH value of a weak base. Look at that. And we can give examples of ammonium hydroxide, calcium hydroxide, and magnesium hydroxide. Very good. Very good. So sodium hydroxide and potassium hydroxide can get ionized. They'll give rise to a higher concentration of hydroxide ions. So the higher the concentration of hydroxide ions from these substances on ionizing, the stronger the substances in terms of their basicity or in terms of their alkalinity. And you see, you should note this. When a base dissolves in water, it gets called an alkali. An alkali. An alkali is a soluble base, a base that dissolves in water. Look at that. So sodium hydroxide and potassium hydroxide can dissolve in water. They are called alkalis. Alkalis, or an alkali being a soluble base. When they dissolve in water, they give rise to sodium ions, potassium ions, hydroxide, and then hydroxide ions. The hydroxide ions they are producing are of a higher concentration. So sodium hydroxide and potassium hydroxide ionize completely, ionize fully. Look at that, ionize wholly to give a higher concentration of hydroxide ions. They become strong bases. Their pH must be 12, 13, or 14 because of the higher concentration of hydroxide ions. I guess you're getting the point. But now, if I talk about ammonium hydroxide, calcium hydroxide, or magnesium hydroxide, these are weak bases. Okay? So they must have a pH of around 8, 9, 10, or 11. Them being weak bases and having a pH of 8, 9, 10, or 11 will make them to ionize or dissociate in water partially or incompletely to give a smaller concentration of hydroxide ions. The stronger the base, the complete dissociation will actually undergo. The higher the concentration of hydroxide ions. The weaker the base, the incomplete dissociation that it will actually undergo, the smaller the concentration of hydroxide ions. So I expect in my discussion to have this. Weak bases, pH ranging from 8, 9, 10 to 11. Strong bases, pH ranging from 12, 13, and 14. But again, if it is a strong base, it must ionize completely to give us a higher concentration of hydroxide ions. But if I talk about ammonium hydroxide, and it dissociates, it's going to give me ammonium ions and hydroxide ions. So we'd actually say that this compound has not dissociated completely. If it does not dissociate completely or it partially dissociates, it will give us few hydroxide ions. If it gives us few hydroxide ions, it will have a lower pH of 8, 9, 10, or 11. And obviously, it becomes a weak base. It becomes a weak base. Just like the way acids behave as electrolytes, when a base is weak, we shall have a smaller deflection on the ammeter. A smaller deflection on the galvanometer. The bulb ends up becoming less bright. And we shall have a smaller reading on the voltmeter. If the base is stronger and it dissociates completely or fully or wholly, we shall have a greater reading on the voltmeter, a greater deflection on the galvanometer, a greater deflection on the ammeter, or the bulb becomes very bright, or the bulb becomes brighter. So that's the difference between weak bases and strong bases. Weak bases and strong bases. Now, there's something else that I'm supposed to actually introduce to you, which is very, very important. Very, very important that you also need to know as you actually come to an end of this topic. So you should also note that we have types of solvents in this topic, because of course this base and these acids can also be solutions. So it must not actually allow us not to discuss this again as a very important area to consider. You see, you know what you need to know is this. A solvent is just a liquid. You see, and the liquid can either be polar or non-polar. That matters a lot. A liquid can either be polar or non-polar. Now, you see, you'll wonder, why would I actually call a substance or a liquid or a solvent polar and decide to call the other one or the other substance as non-polar? What brings out the difference between these two in as far as our today's discussion is concerned? What you need to know is this. A substance is referred to as polar if, one, if I take an example of water, water has oxygen atoms and hydrogen atoms. Hydrogen atoms are partially positive and oxygen atoms are partially negative. So that a structure of this caliber can be of this type. I can have one oxygen, this means delta, and the charge is 2 negative, because oxygen is number 8, so it has to have 2 to 6. So for it to be stable, it requires 2 electrons, because the second energy level must have 8 electrons. So it ends up having a charge of 2 minus. Then we are actually attaching these to a hydrogen, which is partially positive, partially positive. So there's a shared pair of electrons, correct? And a shared pair of electrons as well. Because between a hydrogen and oxygen, we have what you call a covalent bond. Why? Because they are all nonmetals. And in nonmetals, we have what you call a covalent bond, where there's what you call equal sharing of a pair or pairs of electrons. So between O and H, there's a pair of shared electrons. Between this same O and another H, we have what you call a shared pair of electrons. So a water molecule having 2 hydrogen atoms and 1 oxygen atom. Correct. So, why would I call water a polar solvent? Because water is partially positive and partially negative. In this bonding process, oxygen is more electronegative. Oxygen is more electronegative, to mean it attracts this shared pair of electrons onto itself more strongly than the way hydrogen does it. So, oxygen has a greater affinity for the shared pair of electrons. So it ends up attracting those electrons onto itself more strongly, and that makes it to become more negative. Hydrogen has a low affinity for those shared pair of electrons, so it becomes more positive. At the end of the day, the water molecule becomes partially negative and partially positive. It becomes a polar solvent. I don't know if you're actually getting the point. What am I trying to say? Water has 2 hydrogen atoms and 1 oxygen atom. In the bonding process, there's a shared pair of electrons between every hydrogen and the oxygen atom in the water molecule. But now, oxygen attracts the shared pair of electrons onto itself more strongly than hydrogen. And because it strongly attracts the electrons onto itself, it becomes negative. Hydrogen, which is less able to attract the electrons, becomes positive. So oxygen atom develops a partially negative charge, while hydrogen atoms develop a partially positive charge. So a molecule or a substance or a solvent or a liquid that behaves like water, where it is negatively charged in one end and positively charged in the opposite end, is said to be polar. So water therefore becomes a polar solvent. For the shared pair of electrons, oxygen is strongly able to attract the electrons. Hydrogen atoms are less strongly able to attract the electrons. So they develop a partially positive charge. This one develops a partially negative charge. So this substance is partially negative at one point and partially positive on this other point. It becomes a polar solvent. Okay, if you look at hydrogen chloride, if I may proceed, hydrogen chloride is also a polar solvent. Why? I can decide to dissociate this one into hydrogen ions, then chloride ions. Look at that. You can realize that it is partially positive at one end and partially negative on the other end. So it becomes also a polar solvent. A substance that is actually partially positive at one end and partially negative on the other end gets called a polar substance or a polar solvent if it is a liquid. And this is because chlorine has a higher affinity for the shared pair of electrons. To explain this, I'm going to say chlorine has a greater affinity for the shared pair of electrons. Hydrogen has a low affinity for the shared pair of electrons. So the one that has a greater affinity for the shared pair of electrons becomes partially negative. The one that has a low affinity for the shared pair of electrons becomes partially positive. So it makes the substance to become partially positive and partially negative at one end and the other end respectively, making the substance to become a polar substance. Making the substance to become a polar substance. So I'll actually have this at the end of the day. H with a partially positive charge and chloride with a partially negative charge. Correct. That makes that substance to become a polar substance. Become a polar substance. Okay, so we can be able to actually say that polar substances can dissolve in polar solvents. How? Let me have this. I have oxygen, it is partially negative in the water molecule. I guess you can see, yes. Then we have hydrogen, which is partially positive, and again hydrogen, which is partially positive. So if I decide to solve hydrogen chloride or hydrochloric acid in the water, what happens? The partially negative hydrogen from the acid is attracted onto the negative part of the water molecule. The partially negative part of the acid is attracted onto the partially positive part of the water molecule. The partially positive hydrogen is attracted to the partially negative oxygen in the water molecule. Then the partially negative chloride is attracted to the partially positive hydrogen in the water molecule. That makes now the substance, now the hydrochloric acid, to dissolve in the water. That's how it works. So the partially positive part of the acid is attracted to the partially negative part of the oxygen in the water molecule, and the partially negative part of the acid is attracted to the partially positive hydrogen in the water molecule. That makes now the acid first to dissolve and then to dissociate. Okay, why do I call this a polar substance? Now the hydrochloric acid. Hydrochloric acid is a polar substance because one, it first dissolves in the polar solvent, now the water. After dissolving in the polar solvent, it ionizes or it dissociates to give us hydrogen ions, then chloride ions. So a substance that can first dissolve in a polar solvent and then later on dissociate or ionize is called a polar substance. Is called a polar substance. So hydrochloric acid first dissolves in the water. Dissolving, it ionizes or dissociates, where the hydrogen ions are attracted to the negatively charged part of the water molecule, and the chloride ions are attracted to the positively charged part of the water molecule, making the substance to ionize in the water. So that means the covalent bond between the hydrogen ions and the chloride ions is broken. And on breaking, those ions with opposite charges are attracted to the partially positive part of the water molecule and the negatively charged part of the water molecule. That makes it possible for us to end up having acidic properties getting seen. To mean the solution now becomes acidic. Why? We have hydrogen ions from the acid. In that case, you'll find that one, if a moist blue litmus paper is dropped into this solution, it will turn red because the hydrochloric acid first dissolved in the water, then it ended up dissociating, giving us hydrogen ions. And when hydrogen ions are present, it will make the solution to be acidic. And once the solution is acidic, it will turn moist blue litmus paper red. If I drop here metal, there will be effervescence, or fizzing can be able to get observed, or gas bubbles are going to be produced. Why? Whenever a solution is acidic or is an acid, and you add a metal, what did I say in my previous discussion? You're going to form salt plus hydrogen gas. That tells you that you're going to form hydrogen gas. And once hydrogen gas is present, that can be effervescence or gas bubbles getting produced, or fizzing can be seen. And again, if you even put here a metal carbonate into this solution, once you have actually put here metal carbonate, I've actually told you this, whenever an acid combines with a metal carbonate, what do you expect? You're going to expect salt, carbon dioxide, and water. Still, you can actually be able to observe effervescence. You can observe effervescence. Why? Because the acid or the solution is acidic because of the hydrogen ions after dissociating hydrochloric acid. And that acidic solution now can react with metal carbonates to give us salt, carbon dioxide, and water. The carbon dioxide is a gas. It is the one responsible for the effervescence or the gas bubble that get produced during this reaction. The same applies to this. When I drop a metal into this solution, which is now acidic because of the hydrogen ions getting produced from the dissociation of the hydrochloric acid, we shall also observe effervescence because of the hydrogen gas getting produced in this case. Now, you might wonder, why would I not end up having any solution? Let me talk about methyl benzene. Methyl benzene is also a solvent, but the solvent is non-polar. Look at that. So if I add HCl acid, HCl acid will dissolve in methyl benzene, but it won't dissociate. I repeat, methyl benzene is a non-polar solvent. Methyl benzene is a non-polar solvent. When you actually dissolve HCl into this methyl benzene, it dissolves, but it does not dissociate. So it can't ionize into hydrogen ions and chloride ions. That means the solution will be non-acidic. So even if I drop here a blue litmus paper, the paper remains blue. Why? The solution does not have any acidic properties. Now you're trying to compare this with a situation where I'll have a container, then I actually put here water. I know water is polar, being partially negative and being partially positive, as I've actually told you. If I put here HCl, what will happen? What will happen? I've told you the HCl first dissolves. After dissolving, the partially positive part of the acid is attracted to the partially negative part of the water molecule. Then the partially negative part of the acid is attracted to the partially positive part of the water molecule. So it makes the compound to have its covalent bond getting broken. And once the bond is broken, the substance is said to have dissociated or ionized. And once we have the hydrogen ions getting produced here, we shall make the whole solution to be acidic. And when it becomes acidic, it can turn the moist blue litmus paper red, or it can make the solution to react with a metal or a metal carbonate. But in this other case, we are wondering why. It's because of this. Metal benzene is nonpolar. The acid will dissolve in metal benzene, but there will be no ionizing or dissociating of hydrogen ions and chloride ions. The acid remains intact. The ions remain intact. No breaking of the covalent bond occurs. So the whole solution does not end up having any acidic properties. So the blue litmus paper remains blue because the solution is not acidic. Yeah, that brings out the difference between a polar solvent and a non-polar solvent. And remember always to handle metal benzene with a lot of care because it is very, very, very poisonous. So in other words, metal benzene is a non-polar solvent. It can allow the acid to dissolve into it, but it being nonpolar, it does not dissociate the hydrogen ions and chloride ions, forming the hydrochloric acid. So the solution ends up having no hydrogen ions. At the end of the day, the solution does not exhibit any acidic properties. So it won't have any effect on litmus paper and does not react with any magnesium metal, for example, or calcium carbonate as a metal carbonate. So there will be no effervescence of an acid having reacted with a metal to give us hydrogen gas as a product, and there will be no effervescence as a result of the acid reacting with a metal carbonate like calcium carbonate to give us a gas like carbon 4 oxide. So let's meet in our next lesson, and I shall be able to embark more on how I can be able to show again polar and non-polar solvents now using bases like sodium hydroxide and ammonium hydroxide. Greetings from Mr. Ngata, and let's proceed with our today's class. And I have to go and look at something else just as a continuation of where we had stopped in this topic called acids, bases, and salts. And I think I'm going to look at how a particular solvent, which can either be a polar solvent or a non-polar solvent, can have an effect on bases. Let me pick a practical example, and let me say I have actually taken this as my container, which is a beaker, and in this beaker I'm going to have, let's say, water. I told you water is chemically written as H2O, and it has the following. It has an oxygen atom, it is partially negative, and 2 hydrogen atoms which are partially positive. And on this other end, we might have another beaker that has methyl benzene, which is a very poisonous substance that needs to be handled with a lot of care. And we have decided to put into this water sodium hydroxide. What is going to happen? And again, you can also put sodium hydroxide in this methyl benzene. So what I'm going to have is this. Sodium hydroxide is first going to dissolve in water. And in this other setup, we will also have the sodium hydroxide dissolving in methyl benzene. Now, where does the difference come in? The difference comes in this manner. In water, which is a polar solvent, or partially negative and partially positive, the sodium hydroxide dissociates or ionizes into sodium ions and hydroxide ions. The sodium ions are surrounded by the oxide, which is negatively charged. Then the hydroxide ions are surrounded by the hydrogen ions, which are positively charged. Remember, the oxide ions and the hydrogen ions are the ions that make up the water in which the sodium hydroxide has been dissolved. So once the sodium hydroxide has dissolved in the water, the sodium hydroxide becomes ionized or dissociated into sodium ions and hydroxide ions. Immediately, the sodium ions are surrounded by the oxide ions from the water, or the sodium ions are surrounded by the partially negative part of the water molecules, while the hydroxide ions from the base, the sodium hydroxide now getting dissolved into this water, are surrounded immediately by the hydrogen ions, which are the partially positive ions from the water molecules. We shall say the solution ends up having alkaline properties. Alkaline or basic properties. Why does the solution end up having the alkaline or basic properties? Because of the hydroxide ions. On the other hand, the sodium hydroxide has dissolved in methyl benzene, but methyl benzene is non-polar. So it is not partially positive and partially negative. So the sodium hydroxide remains sodium hydroxide. So it does not ionize. So it lacks basic or alkaline properties. So the sodium hydroxide has dissolved in methyl benzene, which is a non-polar solvent. But the sodium hydroxide dissolving in methyl benzene does not ionize or does not dissociate. So it ends up lacking any basic properties when dissolved in methyl benzene. So no basic properties or alkaline properties can be experienced in this solution. Why? Because the base dissolved in the non-polar solvent but never ionized. So we do not have any hydroxide ions present in this methyl benzene. So the end product or the solution does not end up having any hydroxide ions. So it lacks the alkaline or basic properties. So that is to tell you that when I place a moist blue litmus paper here, and as well I place here a red litmus paper, you'll realize that because there are hydroxide ions in this solution, because sodium hydroxide has ionized, we shall find that the red litmus paper turns blue to confirm that the solution is alkaline or basic. Why? Because the sodium hydroxide first dissolved in the water, then ionized. On ionizing, it gave out sodium hydroxide ions separately. Sodium ions, then hydroxide ions. The hydroxide ions made the solution to become alkaline, turning the moist red litmus paper blue. When I place here a moist red litmus paper, it remains red. Why? Because the sodium hydroxide dissolved in the methyl benzene, the non-polar solvent, but never ionized. That is to tell you that the solution does not have any basic or alkaline properties because no hydroxide ions are able to get produced or formed in this case. So no alkaline properties are present, and thus the moist red litmus paper remains red. Now, let's go to something else. We've talked about acids, we've talked about bases. We have to go and look at something called amphoteric oxides and hydroxides. Amphoteric oxides and hydroxides. You'll want actually to know the difference between an acid and a base. One can be an acid can dissipate hydrogen ions on dissociating in water. Hydroxide ions are dissipated by a base when that base ionizes in water. But now, what is an amphoteric oxide and as well an amphoteric hydroxide in this manner? Amphoteric oxides and hydroxides are able or can be able to get referred to as substances that react with both acids and bases. Substances that can react with both acids and bases. In other words, if a substance is an amphoteric oxide or an amphoteric hydroxide, then they can react with both acids and bases. You see, and at the end of the day, they actually form salt and water. At the end of the day, the reaction gets called neutralization. So an amphoteric oxide or an amphoteric hydroxide can be a substance or a chemical or a compound that has the ability to react with an acid and as well react with a base to form salt and water, or just to form salt. At the end of the day, it can either form salt and water or only salt, but the reaction is called neutralization reaction. So in other words, something which is amphoteric has both basic and acidic properties. It can behave as an acid and it can as well react as a base or behave as a base. There are three known oxides and hydroxides which are actually amphoteric or which can actually behave as acids and react as bases as well. We have zinc oxide, we have lead, for oxide or lead 2 oxide for that matter. So we have zinc oxide, then lead 2 oxide, then we have aluminium 3 oxide. So zinc oxide, lead 2 oxide, and aluminium 3 oxide are examples of what we call amphoteric oxides. Then we have zinc hydroxide, okay, lead 2 hydroxide, and aluminium 3 hydroxide as amphoteric hydroxides. So just in case a question asks me to give examples of amphoteric oxides, I'll talk about zinc oxide, lead 2 oxide, and aluminium 3 oxide. Lead 4 oxide rarely exhibits amphoteric properties, so it may not form part of this. We'll only talk about zinc oxide, lead 2 oxide, and aluminium 3 oxide, or zinc hydroxide, lead 2 hydroxide, and aluminium 3 hydroxide. Those are the main known oxides and hydroxides that you are supposed to know as a student, because as you prepare to sit for your final examination, you'll be able to actually get to that point of getting told to write a chemical equation involving these oxides and hydroxides with bases and acids. Now, let me assume I have this as my oxides and hydroxides reacting. So let's say we have zinc oxide and lead 2 oxide and aluminium 3 oxide, and I've reacted this with acids. Let's talk about nitric 5 acid. So these ones are going to behave as bases in this case. I've told you, if something is amphoteric, it means it has both acidic, so has both acidic and basic properties. So it can behave as an acid and then behave as a base as well. So you're assuming that these oxides are now going to behave as bases. And you're saying they can be amphoteric oxides or can be amphoteric hydroxides. So something which is amphoteric can be in the form of an oxide or in the form of a hydroxide. But just know it has both acidic and basic properties. So if I say something is amphoteric, that means it has both acidic and basic properties. It can either be an oxide or a hydroxide of a substance. So these oxides are going to behave as bases and they are going to react with this acid. We shall get zinc nitrate as our product and water. Obviously, we know when an acid reacts with a base, it gives us salted water. So this is a solid, this is aqueous, and this is a liquid. Correct. So we put 2 here. Then again, this gives lead nitrate plus water. You can also put 2 here. So you have again aluminium nitrate. Put here 3 plus water. So this is when these oxides are behaving as bases, and in that case they'll give us salt and water. So zinc oxide, lead oxide, and aluminium trioxide are behaving as what? As bases. And they are reacting with acids to give us zinc nitrate, lead nitrate, and aluminium nitrate, which are now salts then plus water in each case. So that at the end of the day we can actually have this. Welcome to this class, and there's a part I'm supposed to look at just to put to an end this topic called acids, bases, and salts. And whatever I want to actually introduce to you is how bases behave in both polar and nonpolar solvents. Of course, we've actually touched on that. Now, I just want to go ahead and look at something else, which is actually amphoteric oxides and hydroxides. To begin us off, I've actually told you that something which is amphoteric is something which is actually able to have both acidic and basic properties. And that tells you that the substance can both behave as an acid and as well behave as a base. And these amphoteric substances are put into 2 main categories. They can either be oxides or hydroxides. I repeat, amphoteric substances have both acidic and basic properties, or they can behave as acids and as well behave as bases, and they can either be oxides or hydroxides. The 3 main non-amphoteric oxides and hydroxides that you can put in our discussion today, as I've actually told you, are zinc oxide, lead 2 oxide, and aluminium 3 oxide. We have zinc hydroxide, lead 2 hydroxide, and then aluminium 3 hydroxide. Those are the 3 main oxides and the 3 main hydroxides that you can be able to call as amphoteric oxides and hydroxides respectively. And when I want to actually see how these oxides and hydroxides can behave, for them to actually qualify becoming both acids and bases, you see, let's begin and see. We've said they behave both as acids and as well as bases. If I talk about zinc oxide, I'll come here and have zinc oxide, for example, reacting with nitric 5 acid. I'm going to form zinc nitrate and water. This is a solid, a metal oxide. This is an aqueous solution. This is also an aqueous solution, and this is a liquid. So that we shall have a salt and then water. So this is behaving as a base, and this obviously behaves as an acid. So when a base reacts with an acid, as you had actually been told in Form 1, you'll always be able to get salt plus water. So in this case, our salt is zinc nitrate, then water. There is an oxidation state of 2 on zinc, and that now becomes the formula of zinc nitrate. Zinc, then nitrate. To balance the equation, you should just put 2 on the nitric 5 acid, and that now gives us what you're supposed to have. Another example, we can use lead 2 oxide, is a solid, plus nitric 5 acid, which is aqueous. We shall obviously be able to get lead 2 nitrate as our salt, and water, which is H2O. So these are liquid, and this aqueous, and this is also aqueous, and lead 2 oxide is a solid. To balance the equation again, you can put 2 on nitric 5 acid. To move forward, we can as well be able to have aluminium 3 oxide as our third amphoteric oxide. Now, when they are behaving as bases and they are reacting with the nitric 5 acid as our acid, which is aqueous, we are going to have lead. In this case, we are going to have aluminium and lead for this case. So aluminium 3 nitrate. Okay, we shall put here 3 because aluminium has an oxidation state of 3, then plus H2O. I'll obviously be able to put here 2 and put here 6. Let me see. 2 aluminium atoms, 2 aluminium atoms, then 3 oxygen atoms plus 18. Those are going to be, so 3 plus 18, that is 21. 3 times 3, that is 9. 9 times 2, that is 18. I'll put 3 on water. Okay, so 3 aluminium atoms, 3 aluminium atoms, 3 plus 18, that is going to be 21. 3 times 3, 9, 9 times 2, 18. 18 plus 3, that is 21 also. 6 hydrogen atoms, 3 times 2, that is 6. 6 nitrogen atoms, 2 times 3, that is 6. The equation is balanced. So that is how we can have the 3 amphoteric oxides, zinc 2 oxide, lead 2 oxide, and aluminium 3 oxide or alumina behaving as bases, and they can react with acids like nitric 5 acid to give us salt and water. Zinc nitrate as our salt, lead 2 nitrate as our salt, and aluminium 3 nitrate as our salt. That's how those oxides can behave as bases. Preferentially, they can as well be able to behave as acids. They can also behave as acids. Let's look at this example. We have aluminium 3 oxide, okay, and zinc 2 oxide and lead 2 oxide. These are 3 amphoteric oxides again. Now they're going to behave as acids. So we can pick a base of our choice. We can use sodium hydroxide as our base. Sodium hydroxide as our base. Sodium hydroxide as our base. So look at that. In the first place, they behaved as bases. In this other case, they are behaving as acids. So if a substance behaves as a base and as well behaves as an acid, then that means that substance qualifies to be called an amphoteric substance. It is amphoteric. Correct. So we will be able to have sodium aluminate plus water. Sodium aluminate plus water. So sodium aluminate plus water. Okay. Then we will also be able to have sodium zinc plus water. So that is plus water. Then this one is going to be sodium zinc plus water. And this is going to be sodium plumbate plus water. So sodium plumbate plus water. Okay. So plus water. So sodium plumbate and sodium zinc plus water, respectively. So to balance the equation, what we actually do, we shall actually be able to come here and just put 2 on sodium aluminate. and we shall put 2 on sodium hydroxide, and then put 2 on sodium hydroxide. 2 aluminium atoms, 2 aluminium atoms, and then we have 2 sodium atoms. Shall put 2 here, so 2 sodium atoms, 2 sodium atoms. Then we have 3 plus 2, those are 5. 2 times 2, 4 plus 1, 5. 2 hydrogen atoms, 2 hydrogen atoms. Okay, let's come here. 2 sodium atoms, 2 sodium atoms, 1 zinc atom, 1 zinc atom. 2 plus 1, 3, 2 plus 1, 3. 2 hydrogen atoms, 2 hydrogen atoms. Also balanced, so we can have also 1 lead atom, 1 lead atom. 1 plus 2 oxygen atoms, those are 3. 2 plus 1, 3. 2 hydrogen atoms, 2 hydrogen atoms. It's also balanced, so you can have solid, solid, solid. This is aqueous, aqueous, aqueous. Okay, aqueous, 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 liquid, liquid, liquid. So this is sodium aluminate, sodium zinc, and sodium plumbate. Those are the 3 salts that you can be able to form in as far as these compounds are concerned. As far as these compounds are concerned. So that is what you're supposed to have. And sometimes you can actually be able to get given this equation. You're told to write a chemical equation between these oxides behaving as acids and reacting with bases like sodium hydroxide together with water. I may just maybe use one example. Let me say I have sodium hydroxide plus let's give an example of zinc oxide. Then we have water. I guess it makes sense. So we have this as an aqueous solution, this one as a solid, and this a liquid. So this behaving as a base, obviously it's a base, and this now behaving as an acid. Then we are going to get the product as Na. Okay. Then 2. Then we shall have zinc, then OH. Then we'll put here 4. Yeah, so we'll put 2 on this. So 2 sodium atoms, 2 sodium atoms. Then we have 2 oxygen atoms plus 1 plus 1. Those are preferably 4. 2 plus 1 plus 1, those are 4. 4 oxygen atoms, okay. 2 hydrogen atoms plus 2, those are 4. 4 hydrogen atoms. 1 zinc atom, 1 zinc atom. This is aqueous. Very good. So that we can be able to call this compound as sodium tetrahydroxo zingate, or sodium tetrahydroxo zinc 2. So sodium tetrahydroxo zingate, sodium tetrahydroxo zingate, sodium tetrahydroxo zingate. I guess it makes sense. So sodium tetra, so that is sodium, then tetrahydroxo, then zingate 2. Because the oxidation state on zinc is 2 positive, so sodium tetrahydroxo zingate 2. Sodium tetrahydroxo zingate 2. Yeah, that's what you can be able to have as far as that equation is concerned. And preferably, assuming you're using what you call hydroxides, and you have this as your equation to write, what you do have, you might actually come up with these equations. Those are oxides behaving as bases, and here behaving as acids. So we can come here and have an equation where they are now able to consider having bases. So you have aluminium 3 hydroxide, lead 2 hydroxide, and zinc 2 hydroxide. they are behaving as bases. So you can react them with hydrochloric acid, so that we can end up having this. So this is hydrochloric acid. So you can end up having this. So we shall have aluminium 3 chloride plus water. Okay, then we have here lead 2 hydrochloride plus water, then zinc chloride plus water. So aqueous is insoluble in water, solid, aqueous, liquid, then liquid. So aqueous, preferably aqueous. So these are behaving as bases, and these are now behaving as acids. Obviously, they'll give us salt plus water. Correct. So that when they are bases, those hydroxides, we talked about amphoteric substances either being oxides or hydroxides. So when amphoteric hydroxides behave as bases, they will react with acids to give us salt and water. And the only products for us to capture in our discussion today. And sometimes they can behave as acids. And when they behave as acids, they can also be able to react and give us products. For example, we can have just one example to help us understand this. Let's say you have lead 2 hydroxide behaving as an acid, and it is reacting with sodium hydroxide. So aqueous, then aqueous. So what do we form as the product? What do we form as the product? Just in case we find these ones reacting as, so we shall form what you call sodium, look at that, 2, then PbO, OH, close the bracket, then put 4. Then we can be able to call this sodium tetrahydroxyplumbate, because Pb means plumbate. Then 2, sodium tetrahydroxyplumbate 2, and this is a complex salt. So this is now going to be a base, and this is now going to behave as an acid. So metal hydroxides can also behave as acids, like lead 2 hydroxide, zinc 2 hydroxide, aluminium 3 hydroxide. They can also behave as what? As bases. So for example, if I have aluminium 3 hydroxide behaving as an acid, so you have OH behaving as an acid, and it's reacting with a base, which is sodium hydroxide. Okay, so we shall have this is also aqueous. We shall also have sodium, then aluminium, of course tetrahydroxo as well, because it is also going to form a complex salt. It is also going to form a complex salt. So that will be NaL, then we can add here OH, then we put them in brackets, then put here 4. So this is sodium tetrahydroxo aluminate. Tetrahydroxoaluminate 3. And again, it's also a complex salt. Tetrahydroxoaluminate 3 as a complex. So I can just put here 2 to balance the equation. 2 sodium atoms, 2 sodium atoms. So this is also aqueous. This is also aqueous. So 2 sodium atoms, 2 sodium atoms, 1 lead atom, 1 lead atom, 4 oxygen, 2, 2, 4 hydrogen, 2, 2. Okay. And this one here, we also need to balance it so that it can be able to. So we have an aqueous solution of aluminium 3 hydroxide. Then we have sodium hydroxide, and we have what we call sodium tetrahydroxoaluminate 3 as our product. One aluminium atom, and we have 3 oxygen and 1 oxygen, those are 4. Then 3 hydrogens, then 1 hydrogen, those are 4. So it's actually balanced. So those are just ways in which you can be able to represent these hydroxides and oxides behaving both as acids and then as bases, to actually refer to them as amphoteric ones. And maybe if you use zinc, you can also have this. You can have zinc hydroxide, now in this case behaving as an acid and reacting with sodium hydroxide, aqueous, to give us sodium and 2 zinc OH, then 4, this is aqueous, so this is sodium, okay, tetrahydroxo zingate 2, sodium tetrahydroxo zingate 2, complex salt also. So this is where now these bases are behaving as acids, and they are reacting with this sodium hydroxide base to give us complex salts: sodium tetrahydroxoplumbate, sodium tetrahydroxoaluminate 3, sodium tetrahydroxozingate 2 as our salts. In this case, as far as these hydroxides behaving as acids is concerned, and remember, on this other side, they had behaved as bases. They behaved as bases where they reacted with these acids to give us salt and water. Salt and water. Salt and water. They behaved as bases. They reacted with acids like hydrochloric acid, we just used here, to give us salt and water. Correct. So aluminium 3 chloride, lead 2 chloride, and zinc 2 chloride were our salts, and the water is also given out during this reaction. But on the other hand, when you look at this other case, they have behaved as acids, and they have reacted with sodium hydroxide base to give us complex salts: sodium tetrahydroxoplumbate 2, sodium tetrahydroxoaluminate 3, sodium tetrahydroxozingate 2 as our products, and as far as this case is concerned. To move forward, we are going to actually look at a subtopic called salt. And of course, you know this, when an acid reacts with a base, you can always get a salt as a product. And for that matter, you can be able now to come here and have this. What is this discussion about? You need to ask yourself, what is a salt? There's a topic in Form 2 called salts. You must have adequately covered that topic, and you can also be able to actually just say that a salt should be an ionic compound formed when a cation from an acid combines with an anion from another compound. Or you can say is actually a compound which is ionic that is formed when you have a cation from a base combining with an anion from an acid. That gives you what you call a salt. So it is first an ionic compound, okay, formed when a cation from an acid combines with, so a cation of choose from a base, preferably, that can be better, combines with an anion from an acid. A cation from a base combines with an anion from an acid. So an ionic compound formed when a cation from a base combines with an ion from an acid. can qualify to be called a salt. For example, HCl is combining with sodium hydroxide. It gives us salt as sodium chloride plus water. This is the cation. Where does it come from? The base. This is the anion. Where does it come from? The acid. So this is our salt. So a salt is an ionic compound. An ionic compound is a compound which is partially positive and partially negative. So a salt is an ionic compound which is partially positive and partially negative, formed when a cation, the partially positive part of that salt, is derived from the base. Look at that. And the anion, the chloride, the partially negative part of the salt, is derived from the acid. So the partially positive part of the salt is derived from the base. The partially negative part of the salt is derived from the acid. It can give you what you call a salt. It can give you what you call a salt. It can give you what you call a salt. Now, you see, you will actually be able to get told one day to define what a salt is. You'll say it's first an ionic compound, partially positive and partially negative. And for us to form this salt, we need a cation from the base and an anion from the acid. Now sometimes you also need to understand this. If I take a compound like sodium carbonate or potassium carbonate, of course everybody knows this reaction is called what? Neutralization reaction. When an acid reacts with a base, it's called neutralization reaction. So, or I take ammonium carbonate and I add to calcium carbonate, or let me even say calcium chloride. And yeah, calcium chloride. You see, if this is the case, you can get products like sodium chloride plus calcium carbonate. Then you can also get potassium chloride plus calcium carbonate. Then you can also get ammonium chloride plus calcium carbonate. What does this tell you? Sodium carbonate, potassium carbonate, and ammonium carbonate are soluble carbonates. They are aqueous. Therefore, calcium chloride is also soluble. It's also soluble. So you can say aqueous, aqueous, and aqueous. Yeah, they're soluble. Calcium chloride is soluble in water. So it's also aqueous. So this is going to be aqueous, aqueous, because sodium chloride, potassium chloride, and then ammonium chloride are also soluble in water. But this is solid, this is a solid, this is a solid. So we shall say the calcium carbonate has been precipitated out. Look at that. In other words, these reactions are called precipitation reactions. So you can put here 2, you put here 2, and then you put here 2 to balance the equation. So in other words, precipitation reactions are also called double decomposition reactions. Double decomposition. They are called precipitation reactions or double decomposition reactions, where you are reacting two soluble salts. So that at the end of the day, you can get one soluble salt and another one is the insoluble salt. So sodium carbonate, potassium carbonate, and ammonium carbonate can be used to precipitate out insoluble salts. Look at that. Sodium plus chlorine, sodium chloride, sodium plus chloride, sodium chloride. So potassium plus chloride, potassium chloride. Ammonium plus chloride, ammonium chloride. These are soluble salts. And now calcium and carbonate gives you the calcium carbonate, the insoluble salt. So precipitation reactions or double decomposition reactions are reactions where two soluble salts are reacted to give one soluble and one insoluble. So it's used to prepare insoluble salts in chemistry. It's actually used to prepare insoluble salts in chemistry. Used to prepare insoluble salts in chemistry. So ammonium carbonate, sodium carbonate, potassium carbonate are soluble salts. They can be used to precipitate out insoluble salts like calcium carbonate, which are actually insoluble in water. Okay, so this means that now we can be able to actually get to that point of realizing that we have majorly only 3 soluble carbonates in water: sodium carbonate, ammonium carbonate, and potassium carbonate. The other carbonates are insoluble. That's why calcium carbonate is actually an insoluble salt. And you see, unfortunately, when you use aluminium carbonate and iron 3 carbonate, you might form acidic solutions that might react with carbonates to liberate carbon dioxide gas. So just in case you might end up forming aluminium 3 carbonate or ammonium 3 carbonate, and you actually dissolve them in water, you realize that aluminium 3 carbonate might hydrolyze out in that water to give us an acidic solution, which again reacts with that carbon dioxide oriented compound like the carbonate to give us now the carbon dioxide gas. That's why we actually preferably say that we might not actually end up having aluminium 3 chloride getting used. Why? Because if you reacted with sodium carbonate, for example, remember this is aqueous, what happens? This one first dissolves in the solution. So it dissolves in the solution to give us an acidic solution, which is going to be aluminium 3 hydroxide plus HCl. Very good. So you can put 3 here also. So this HCl might react with that sodium carbonate. So if you take aluminium 3 chloride, then react with that sodium carbonate and demand to have what you call a precipitation reaction, this aluminium 3 chloride might dissolve in the water in the sodium carbonate to give us aluminium 3 hydroxide and HCl. The HCl formed as an acidic solution can now react with that carbonate to precipitate out carbon dioxide, because you know very well sodium carbonate can react with HCl to give us sodium chloride plus carbon dioxide plus water. So this is aqueous, this is a liquid, this is aqueous, and this is also aqueous. So when you take aluminium 3 chloride, then react with sodium carbonate solution, expecting to have a precipitation reaction, you might observe effervescence of gas bubbles can get produced. Why? Because the sodium carbonate might not react with aluminium 3 chloride, because the aluminium 3 chloride can dissolve in the water within that solution to give us aluminium 3 hydroxide and then HCl. The HCl now might react with that sodium carbonate to give us now carbon dioxide gas, which is actually responsible for the effervescence we are talking about here. Very good. Now this case aqueous. Very good. So that's what you're supposed to know in as far as these precipitation reactions are concerned. Something which is very, very important, because in this case that means you are reacting to soluble salts to get one soluble salt and one insoluble salt. One soluble salt and one insoluble salt. And you see, sometimes you can actually be able to prospectively have a situation whereby sodium hydroxide is used to confirm which ions are soluble and which ions are insoluble in the excess of that solution. What does this mean? It just means that sometimes you need to have this perspective. Let's say, for example, you have to test for the presence of some ions. Let me use an example of zinc. Let me say I have zinc chloride. Yes, it can be seen. Yeah. And the zinc chloride is reacting with the sodium hydroxide. What are you going to get? So this is aqueous. This is also aqueous. So I'm going to have sodium chloride plus zinc hydroxide. So obviously this is insoluble, it will give us what we call a white precipitate. So in other words, we are adding few drops of sodium hydroxide to the zinc chloride. Which ions are present? Zinc 2 ions are present. So when sodium hydroxide is added to a solution containing zinc ions, the zinc ions combine with hydroxide ions in the sodium hydroxide to give us zinc hydroxide. The zinc hydroxide is an insoluble base and it gives us what we call a white precipitate. We are assuming that the zinc hydroxide, now the white precipitate, white PPT, but don't write PPT in the examination, and you're adding to an excess of sodium hydroxide. Excess. What do you form? These are zinc ions still present in the solution, then hydroxide. You can put here 4, then you can have the resultant charge being 2 minus. Okay, this is a colorless solution. Colorless solution. So this is tetrahydroxozingate. Tetrahydroxozingate 2. Tetra 4 hydroxozingate, then 2. Look at that. Tetra 4 hydroxo, that is hydroxide ions, zingate, then 2. And someone can decide to put here sodium ions, no problem. I can put here 2. That still can actually be able to make sense to us. So you can put sodium here, then you put 2 here, then you can put here 2. That still makes sense. But now, as an ionic equation, you can just remove the sodium ions because you're just adding the hydroxide ions. Then put a negative here, remove the sodium here. That can now become your final answer. So you have zinc hydroxide from this. Okay, this one as a white precipitate because it's insoluble in water, and you're adding more hydroxide ions from sodium hydroxide. There's a 2 here to balance the equation. So excess hydroxide ions, of course you're actually taking it from sodium hydroxide. You're adding excess sodium hydroxide. When you add excess sodium hydroxide, you're adding just hydroxide ions. Okay, so that ends up giving you tetrahydroxozingate 2, which is a colorless solution. Tetrahydroxozingate 2 is a colorless solution. Now let's try using a different example, such as using aluminium. We'll take aluminium trichloride for example. Yeah, it has aluminium ions. We are adding to sodium hydroxide. We're talking about few drops. What do you get? Aluminium 3 hydroxide plus sodium chloride. This is also a white precipitate. So aqueous, and real aqueous. So just put here 3, then put here 3. Balance the equation, and you can decide now to add excess sodium hydroxide. So you pick this aluminium 3 hydroxide. You are adding excess hydroxide ions. So we know it is sodium, so excess. So in excess, this was in few drops, case these are now in excess. So this gives us now aluminium OH, then 4, then that gives us what? That gives us aqueous, then we have a resultant negative charge on top. This is also aqueous, this is also aqueous. Okay, it's also going to be colorless. This is also tetrahydroxoaluminate 3. tetrahydroxyl 3. So we'll now be able now just to have this one getting balanced already. 3 hydroxide ions plus 1 hydroxide, those are 4 hydroxide ions. It's balanced. Tetrahydroxyl 3 as our equation, as our resultant equation, as our resultant equation. To proceed with our topic, we can now be able to go to something else. And today I want us to just finalize on what we were discussing under acids, bases, and salts. So I'd want to just introduce some more complex salts, then you can be able to see where they can be found and their applications in our environment or in our society. And we might have a good example like this. That is zinc. Then we have ammonia. And this, and you can have this. Okay. Then you can also have these. So these can be 2 plus. And then you can also be able to have copper. Then you have ammonia. Then you can have 4. And you can have 2 plus. So this is tetraamine zinc 2 ions complex salt. So tetramine zinc 2 complex salt. This is tetraamine copper 2 complex salt. So this tetraamine zinc 2 and tetraamine copper 2 are formed when ammonia solution is added to a compound containing zinc ions and copper ions in excess. An excess of ammonia solution is added to a compound or compounds containing zinc ions and copper 2 ions. So this is a colorless solution. We must have done this under nitrogen of its compounds, and this is a deep blue solution to confirm that copper 2 ions are present. Deep blue solution. So tetraamine zinc 2, tetraamine copper 2, deep blue and colorless. Some of these compounds can be found in some naturally existing compounds in both plants and animals or molecules. Kwa mfano, you can actually say, if I go to plants, I'm going to get a molecule called chlorophyll. If I go to animals, I'm going to get a compound called hemoglobin. I think you might have heard of a chance getting some compounds like chlorofluorine, hemocyanin. So hemoglobin is the red pigment, which is a protein that gives the blood its red color, and it combines with oxygen, transporting oxygen around the body. Chlorophyll is the green coloring matter in plants found in an organelle or structure in the cell called chloroplast, and this is the one that absorbs sunlight so that the plant can be able to manufacture food. So some of these complex salts like tetraamine zinc 2 and tetraamine copper 2 can be found in chlorophyll and hemoglobin. They're actually very, very important compounds in as far as plants and animals are concerned. Some of these other complex salts can be used in softening of hard water in ion exchange. So in ion exchangers, just take note of this. In ion exchangers, you can find some of these complex salts getting used in softening of hard water. Softening of hard water. So they can be used to soften hard water. And you see, that means if salt is found in water, it can make water to be salty. So that gets called hard water. To remove the hardness in water, that means to precipitate out magnesium ions, for example, and calcium ions. Remember, if water is hard, it might have some salts, or it may have some salts. Some salts can be of magnesium and some can be of calcium. So salts such as magnesium salts and calcium salts can be found in water, making the water to be hard. To precipitate out these magnesium salts and calcium salts from the water, we require complex salts as well. And these complex salts can be made of tetramine zinc 2 and tetramine copper 2. So the first role of complex salts like tetramine zinc 2 and tetramine copper 2 is for them to form part of what you call the chlorophyll and the hemoglobin, which are very complex compounds found in both plants and animals with very appropriate and useful ways you can be able to actually have. Number 2, used in ion exchangers. Ion exchangers. And in ion exchangers, they can be used to actually ensure that they have ended up removing the hardness in the water, so that the water can end up becoming very useful to actually help the plants and animals to have water free from salts. You see, and that means you can be able to actually end up having a situation where the water is softened. The water does not end up having the salts. So you can have magnesium ions and calcium ions getting removed from the hard water, so the water becomes soft water. And to remove the salts from the water, you require complex salts like tetramine copper 2 and tetramine zinc 2. Lastly, you can be able to use these complex salts to be able to remove or to extract metals from their ores. For example, it is actually very known that creolite is an ore that contains aluminium. It is written as NaAlF6 as creolite. Basically, it's a source of aluminium. To extract aluminium from this ore called creolite, we require complex salts. So creolite, 2 sodium atoms, 1 aluminium atom, and 6 fluorine atoms can be a source of aluminium. And for us to extract this aluminium from this creolite, we require complex salts like tetramine zinc 2 and tetramine copper 2. In terms of solubility of salts, you'll actually realize that some salts will have to have the temperature increasing before they can actually increase their solubility. That means how much of a salt can dissolve in water. For example, if I draw a curve of this type, I'll realize that this can be potassium chloride 5. You must have met it somewhere under nitrogen is compounds in terms of forming what you call bleaching agents like sodium chloride 5, sodium chloride, sodium hypochlorite, sodium chloride 1. So this is called what you call sodium chloride 5. So this is solubility. That solubility can be measured in grams, 100 grams of water. How much of a salt in grams can dissolve in 100 grams of water? And this can be the change in temperature. So in other words, when temperature increases, look at that. The temperature of potassium chloride 5 increasing, that is, the solubility of that salt also increases. Now, potassium chloride can also have its solubility increasing when temperature increases, but it is lower than that of potassium chloride 5. That means at a very high temperature, potassium chloride 5 dissolves faster in water. Potassium chloride also dissolves in water, and with the temperature increases, that solubility also increases. Salts like sodium chloride and calcium sulfate will not have any of the solubility changing when the temperature increases. That means the solubility remains constant even if the temperature increases. Now, potassium nitrate will also have its solubility increases when the temperature increases. So potassium nitrate also have its solubility increasing when temperature increases. So potassium nitrate, potassium chloride 5 will have the solubilities increasing when temperature increases. Potassium chloride also have its solubility increasing when temperature increases. Sodium chloride and calcium sulfate will have their solubility remaining constant even if temperature increases. Very good. Now, when temperature increases, you'll have a salt like calcium ethanoate. You see, increasing its solubility. That means even if the temperature decreases, calcium ethanoate can have its solubility increasing. Very good. So this is calcium ethanoate. The solubility of this salt increases when temperature decreases. So that means when temperature increases, then the solubility will decrease. An increase in temperature will increase the solubility of potassium nitrate, potassium chloride 5, and potassium chloride. When temperature increases, the solubility of sodium chloride and calcium sulfate remains constant. When temperature increases, that means the solubility of calcium ethanoate decreases. That's the summary of the solubility of salts as far as the change in temperature is concerned. Maybe to actually bring you to some attention here, you can have any question of this type or a graph with solubility here in grams per 100 grams of water, and this is the curve that can be potassium chloride, potassium nitrate, potassium chloride 5. Then this is 40, so you can have here like 37, if I'm not wrong, 37 maybe grams, maybe this is 20, this is 40. Then we can have here a temperature of around 30 degrees Celsius. Then you can also have something of this sort here. Then you can have maybe a temperature of around 60 degrees Celsius. Then you have 40 grams, of course. So they can maybe say if a saturated solution, a solution is saturated if it cannot dissolve any more of the solid or the solute or the salt at that given temperature. So if I say a solution is saturated, that means if this is my container, I've placed here some water and the salt, and I realize that this solution is saturated. That means this solution cannot dissolve any more of the solid, cannot dissolve any more of the solute at that given temperature. So it can't dissolve any more of the solid, it can't dissolve any more of the salt, or can't dissolve any more of the solute at that given temperature. So how much of the salt crystallizes out if the solution is cooled from 60 to 30? At 30, only 37 grams of the salt has dissolved. Okay, so let's just give this practical example. Let's say this is solubility in grams per grams of water. Then this is 37 degrees Celsius. Then 40 degrees Celsius, that is temperature. So, what do you expect? At 37 degrees Celsius, 30 grams has dissolved. At 40 degrees Celsius, let's say maybe 60 grams has dissolved. So if the solution is cooled from 37 to 40, or now cooled from 40 to 37, how much salt will crystallize out? So at 40 degrees Celsius, 60 grams has dissolved. At 37 degrees Celsius, we have 30 grams dissolved. So if we cool this saturated solution that cannot dissolve any more of the solid from 40 degrees Celsius to 37 degrees Celsius, how much salt will crystallize out? We shall just get the difference. So we shall have 30 grams of the salt crystallizing out. So when you're told that a salt is dissolved in water and then the solution becomes saturated, that means that solution cannot dissolve any more of the solute. It is actually saturated. It has more of the solute at that given temperature. And addition of more salt cannot dissolve that salt anymore, because the solution is already having enough of the solute or the salt. So it can't dissolve any more of the salt of that salt at that temperature. So if cooling gets done maybe from 40 degrees Celsius to 37 degrees Celsius, and you want to see how much of the salt can come out of that solution, Just take the solubility at that higher temperature, then subtract the solubility at that lower temperature after cooling has actually occurred. You get the much of the salt that can actually precipitate out or crystallize out. And that's why you actually end up having what you call fractional crystallization, which means you're actually using what you call the difference in the solubilities of the salts in the same solvent to separate them. So the separation of different salts by making use of the difference in solubility in the same solvent is what we refer to as fractional crystallization. Remember, we might have a curve of this type, and this is our first salt, and this is our second salt. This may be salt X and this salt Y. So at a particular temperature, the salts have different solubilities. Look at that. That means the separation of two salts, such as X and Y, by making use of the difference in the solubility in the same solvent, like water, is called fractional crystallization. You make use of the difference in the solubility of the salts in the same solvent at a particular temperature to separate them. Let me give you a table that can give us a summary of what I'm trying to say. Let me say we have been given this table. Let's have a look at it. Then this is the salt. Guess you're going to understand what I'm trying to say. Then we are told that this is potassium nitrate, for example. You can pick this to be potassium chloride 5. Of course, at a higher temperature, this is more soluble. At a lower temperature, this is actually also with an increasing solubility. Look at this. Potassium nitrate is more soluble, and this one is less soluble when the temperature increases. Now, we can have a temperature like 50 degrees Celsius, and this is solubility, of course, at different temperatures. Maybe this can be 20 degrees Celsius. You can have 86 grams, 31 grams. You can have 18 grams, then 8 grams. So someone can ask you, if the mixture is cooled from 50 to 20, you are cooling this mixture of these two salts from 50 degrees Celsius to 20 degrees Celsius. We're going to use what we call fractional crystallization. Fractional crystallization. What is fractional crystallization? The use of the difference in the solubility of salts at different temperatures to separate them if they are put in the same solution. Now, from 50 to 20, which salt crystallizes out? Let's begin in this potassium chloride 5. At 50, 18 grams is dissolved. At 20, 8 grams is dissolved. So how much salt comes out? We shall say 18 grams minus 8 grams. So 10 grams of potassium chloride 5 comes out. Look at that. 10 grams of potassium chloride 5 comes out when the solution is cooled from 50 degrees Celsius to 20 degrees Celsius. What about potassium nitrate? At 50 degrees Celsius, 86 grams has dissolved. Minus. At 20 degrees Celsius, 31 grams is dissolved. So how much has come out? If this one is still dissolved, and the solution is cooled from 50 degrees Celsius to 20 degrees Celsius. So at 50 degrees Celsius, 86 grams is dissolved. At 20 degrees Celsius, only 31 grams is dissolved. So how much salt has actually come out? You just take this minus this. You're going to get 57 grams. 57 grams. So 57 grams of potassium nitrate comes out, or crystallizes out. Then 10 grams of potassium chloride 5 comes out. And the solution is actually cooled. And the solution is actually cooled. So this knowledge can be used. For example, when you want to separate soda ash and sodium chloride in Lake Magadi. Soda ash is preferably sodium carbonate. Okay, then we have sodium hydrogen carbonate, and they have two molecules of water of crystallization. So soda ash having sodium carbonate, sodium hydrogen carbonate, with the 2 molecules of water of crystallization, and sodium chloride. So these two are able to have different solubilities. For example, this is soda ash. This is common salt. They are both found in Lake Magadi. How can we separate the two? You see, when the temperatures are low at a particular time, one salt will crystallize out and the other remains in the solution. When the temperatures are high, on the other hand, one salt crystallizes out and the other remains in the solution. For example, during the day when the temperatures are high, sodium carbonate crystallizes out because its solubility is low at high temperatures, while common salt remains in the solution. At night, when the temperatures are low, sodium chloride crystallizes out while sodium carbonate remains in solution. So during the day, when temperatures are high, sodium carbonate, sodium hydrogen carbonate, the 2 molecules of water crystallization crystallizes out because it is soluble at low temperatures. Then at night, sodium chloride crystallizes out because it's soluble when temperatures are high. So they can get sodium carbonate, sodium hydrogen carbonate, the 2 molecules of water crystallization during the day when temperatures are high, because its solubility engages with the low temperatures. So at high temperatures, it crystallizes out. At night, when the temperatures are low, sodium chloride or common salt crystallizes out because its solubility is high at high temperatures. So at night, when the temperatures are low, the sodium chloride crystallizes out. So they can separate this and separate this. Which process are they actually using? Which method are they actually using? Fractional crystallization. The solubility of 2 salts are different at a particular temperature in the same solvent. So when you go to Gomeni salt works, for example, seawater that has much of the salt is pumped into shallow ponds and evaporation occurs. And at the end of the day, naturally, the crystals just come out. And sodium chloride crystallizes out because of the increase in its concentration. At night, this is more soluble. This is less soluble, it gets obtained. During the day, this is more soluble, this is less soluble, it crystallizes out. It's able to actually get obtained. There's something called hardness of water. And some substances are found in water. Confano, you can see, for example, calcium hydrogen carbonate, calcium sulfate, and magnesium sulfate are found in water. When they are found in water, they make the water to be hard. So there's something called hard water. Hard water. Hard water. Hard water, you said, has calcium sulfate, okay, magnesium sulfate, and sodium hydrogen carbonate. They make the salt to be present in the water and the water becomes hard. And when you use distilled water, water with no salts, the salt lathers easily with the soap. But if you have hard water containing calcium sulfate, magnesium sulfate, sodium hydrogen carbonate, that water won't lather easily with soap. You get the point? So water containing calcium ions, magnesium ions, look at that, will not lather easily with soap because those ions make the water to be hard water. But water containing sodium ions and zinc ions does not make this water to become hard water. The water can easily lather with soap. So these ions can react with soap, and the soap may not lather easily with the water, and they form what you call a scum. You know the point? Which is an insoluble substance. Look at that. And that means you can end up having now this hardness becoming a problem because the hard water is water that does not readily lather with soap, So, but soft water we readily lather with soap. So hard water can waste soap. But this one can save soap because it lathers easily with soap. Lathers easily with soap. You see, we have two main types of hardness. We have what you call temporary hardness. This is hardness that can be removed by boiling. When you have water that has temporary hardness, you can just boil that water and hardness disappears. For example, in this case, when the water has calcium hydrogen carbonate or magnesium hydrogen carbonate, this water has temporary hardness. To remove this hardness, which is temporary, you just boil and hardness is removed. And hardness is removed. But permanent hardness is hardness that contains calcium sulfate and magnesium sulfate. You cannot remove this hardness by boiling. Boiling does not remove the hardness. So that's the difference between permanent hardness and temporary hardness. Temporary hardness contains calcium hydrogen carbonate and magnesium hydrogen carbonate. You can remove the hardness by boiling, but permanent hardness has calcium sulfate and magnesium sulfate as the salts found in that water, and you can't remove that hardness by boiling. It is very difficult for you to remove the hardness by boiling. Now, what are the disadvantages of hard water? Disadvantages of hard water. Number one, disadvantages of hard water include waste soap. That's the first disadvantage. Number two, stains white clothes. Stains white clothes. Then you can say you can also have deposition of fur, of course, on kettles, pipes, and of course electric heaters or boilers. Kettles, pipes, or even boilers that can allow this water to pass through them. And we are actually having staining white clothes because of the scum that gets formed. And the scum is formed when the calcium ions and the magnesium ions react with the soap. They end up forming scum. So when the calcium ions in the water and the magnesium ions in the water react with the soap, they form something called scum. Scum is an insoluble substance. That substance is actually deposited on the clothes, and the clothes become stained. So when fur is deposited on these kettles, pipes, and boilers, and of course fur is just calcium carbonate. When it gets deposited on kettles, pipes, and boilers, it will lower the efficiency of these heating substances and even make these pipes to burst. This is an electric kettle that actually serves as an electric heater or electric heating substance or item, and you're putting here water and you heat it. It may not actually end up having all its current passing through it and having the heat reaching the water. What happens at the end of the day? That can be our electric kettle or electric boiler. Then there is fur or calcium carbonate getting deposited here, and this is the source of current. When the current reaches here, it gets blocked by this fur or calcium carbonate. So the water in this electric kettle cannot actually have all the heat. So its efficiency is lowered. But still, we have advantages of hard water. So what are the advantages of hard water? Remember, it has calcium and is responsible for strengthening of bones and teeth. Strengthening of bones and teeth. So you can actually be able to have the calcium ions getting very, very, very appropriate uses in making our bones strong, and as well making our teeth to also be stronger. So the hard water can be drunk. It has a very sweet taste, and it actually ends up giving us calcium ions, which can strengthen our bones and be able to also strengthen our teeth. And then hard water can also dissolve many substances, but the advantage is that it cannot dissolve some lead from lead pipes. You see, there's no contact between the water and the pipes and lead. So if this is the pipe and we have the calcium getting deposited, the calcium carbonate, the Fa, and the water is flowing, this hardness has prevented any contact between the water and the lead pipes. So the lead is not dissolved along the lining of the pipes. So that can actually provide some protection on the lead pipes, and that's very, very useful. So the hard water has calcium carbonate, for example. Calcium carbonate can get deposited on the lining of the pipes. So there's no any contact between the water flowing through the pipe and the lining of the pipes that actually gets made of lead. So lead is not dissolved as far as these pipes are concerned. People have actually used hard water also in beer brewing because of the calcium and the magnesium ions present in the hard water. Correct. Now, how can we remove the hardness in the water? Hardness in the water can be removed in several ways. It's good that you get actually to that point of knowing some of the ways in which you can be able to use this to remove the hardness in the water. For example, people have ended up using boiling to remove hardness in water. So removing water hardness. Removing water hardness. So boiling can work. For example, if you have calcium hydrogen carbonate and you have to remove the hardness, this can be used to remove temporary hardness. Remember, you can have calcium carbonate, water, and carbon dioxide. That can be a way in which you can be able to remove the hardness in the water. Yeah, there's something called distillation as the second method. The distillation, I think, is a method that removes both types of hardness, but it's very expensive. So this one is only for temporary hardness. This one you can use it for both temporary and permanent hardness. Distillation can be used for both temporary and permanent hardness. So you can also add sodium carbonate to remove hardness in water. And this, you can have the calcium ions and the magnesium ions getting precipitated out by the sodium ions from the sodium carbonate. And that can actually be able to get to that point of getting used to remove also the hardness in the water. It can serve to help us remove the hardness in the water. Then you have what you call the ion exchanger, where you can have this as your ion exchanger. Then you can have these with the sodium ions. So sodium ions, sodium ions, sodium ions, and sodium ions. Then you can actually allow the water to pass through this ion exchanger. Remember, the water has the calcium ions and magnesium ions. So as the water passes through this ion exchanger, the calcium ions are exchanged the sodium ions. So whatever comes out is the water with the sodium ions. Calcium ions have been left in this chamber, and magnesium ions, ion exchanger. So to actually make this ion exchanger to be more efficient, a concentrated solution of sodium chloride is allowed to pass through this ion exchanger so that all the calcium and magnesium ions are washed out, and the area again within this region ends up having more of the sodium ions to remove the excess of the calcium and the magnesium ions in the salt. Then you can also use what you call calcium hydroxide to remove hardness in the water. For example, using calcium hydroxide as another way of removing hardness in the water, and you're adding to, let's say, calcium hydrogen carbonate. Maybe you're removing temporary hardness. You'll end up having calcium carbonate plus water. You've removed the hardness, so you can put here 2, you can put here 2 also. So calcium hydroxide can also be used to remove hardness in the water. By having a reaction between calcium hydroxide, now the one you're using, which is called select lime, and as well calcium hydrogen carbonate to remove the hardness in the water. So aqueous, there's a solid, is liquid, water. Then you can also use ammonia solution. For example, you can have ammonium hydroxide and calcium hydrogen carbonate. Okay, so you can also have that as an equation. You can have calcium carbonate plus water, of course, and ammonium carbonate. That can be a very good equation that can actually represent how ammonium hydroxide can also be used to remove hardness in water. Very good. You can also put here 2. So those are the ways in which you can be able to remove hardness in water. And that marks the end of our topic.